My name is David Hill. I'm a volunteer with the Ventilation Committee for TECA. We're here to do a fan performance demonstration as outlined in our Ventilation Guidelines course. On page 14A, this has been graphically shown in what we're going to do today. We have an 85 cubic foot per minute bathroom fan, one zone, a principal fan, discharging through a duct, a measuring section, and a second duct. The two instruments are, the one on your left is measuring the static pressure, which is the pressure the fan must develop in order to move air through the resistance of the duct and the turbulence of the measurement section. This gauge over here is indicating the flow rate of the fan. So the higher the needle goes here, the more airflow in cubic feet per minute is flowing through this system. Those are the two extreme conditions that we will use today. This fan is running in an almost wide open condition right now, where the static pressure is running at 0.1 of an inch, which is the pressure needed to overcome the resistance of the ductwork and the turbulence of the measuring section. It's close to wide open condition, but already you can see that 0.1 of an inch is still 50% of the allowable 0.2 that is written into the BC Building Code. The extreme opposite condition is if the duct is completely closed off, the fan wheel accelerates to higher RPM, the pressure comes up to shut-off condition, and the flow rate goes to zero. Each of the fittings that we will attach to this ductwork will show that the fan performance is reduced. If we were to install two elbows on this fan, a discharge hood to the outside, 4-inch flex, 3-inch flex, a louver, a soffit louver, or a plug vent. Each of these will have an effect that we can demonstrate now one by one. Our starting point for this demonstration is the fan running in a near open condition with only a short bit of resistance incurred by the duct and the turbulence from measurement. Our first step is to introduce two elbows. We can see that the static pressure goes up and the flow goes down. Not too serious, but it's definitely measurable. And each of these 6 steps, they're all additive effects, that each one diminishes flow and increases the static pressure. Our next demonstration is our 4-inch galvanized sheet metal hood. Again, it has a measurable effect because the air is having to change direction to go through the hood and go through a screen. The third item is a piece of 4-inch flex duct. It's only 3 feet long, which is very short for the real world, but it's possible to see the drastic effect that it has, again, in diminishing the flow and increasing the static pressure. That's only 3 feet. Many fans years ago were ducted in 3-inch flex, which behaves like 2 inches sheet metal. For this demonstration, we have a 4:3 taper, and you can see the very drastic effect that only 2 feet of flexible duct has on the increase in static pressure, reduction in flow. The next item is a louver, often used in soffits. When the louver is put across the end of a duct or an elbow, again, it has a very, very significant effect on increasing the static pressure, reducing the flow, and in this case, generating noise. And I should mention that's when this louver is clean. It only gets worse with time as it gets dirtier. The last thing that's almost never used today are plug vents. There's a 4-inch diameter one, and you can see the static pressure has gone right off the deep end, way beyond the 0.2 of the code, and the flow rate has gone right into the basement as a direct result. The BC Building Code dictates the capacity of this fan, the principal fan, on the bedroom count, and a small factor on square footage. And that fan has to be chosen on the ability to move that much air at 0.2 of an inch of external static pressure. You also, however, must attach duct to that fan which does not exceed the 0.2, so we have tables for both smooth duct and flex to ensure that you stay within that external static pressure limitation.